Right. So I'll just do the acknowledgement of country. We acknowledge and pay our respects to the Kaurna people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Kaurna people to country. We respect and value their past, present, and ongoing connection to the land and cultural beliefs. I just realized that I was about to interrupt. Okay. Sorry. So today we're having Chris Kirkland from the University of Kirkland University talk to us. He's got a very provocative title, and if you were paying attention to the slides, I'm sure they'll also be provocative. Maybe that's what I've been told by other people. Deep time, deep space, deep impact. So Chris is the director of the Kirkland Frontier Institute for Geoscience Solutions and the founding leader of the Timescales of Mineral Systems Group at Kirkland University that was established a decade ago now. He's an expert in isotope geology, applying diverse techniques to address fundamental questions and deliver meaningful data sets that support mineral exploration across national and deposit scales. Thanks, Chris. Off. Let's do the next song and dance. Oops. There we are. Sorry. Hide video panel. Okay.
Awesome. Well, it's a great pleasure to be here. I'm excited to come across to Adelaide. Lovely city, lots of good friends over here. And I think with that in mind, that's given me a little bit of a license to be a little bit more provocative with this talk, hopefully. So I have got something to hide behind here. So if things are thrown at me, should be okay. So what I'd like to do today is maybe encapsulated in this. Well, there we go already. Let's go back. Maybe encapsulated in this beautiful mural. So it's a NASA mural, and it talks about, you know, our relationship to space, but not only space, the galaxy, early Earth, and then potentially leading all the way through into the evolution of life. Right out the far end of this mural, near where the cafeteria is, actually, you can see there's even cavemen. So it's this beautiful mural that takes us through, you know, the Ediacaran period, through the stromatolites, into the Precambrian, the dawn of life in this maybe slightly more hellish early situation, but we do have a water world here, and maybe there's some influence of other processes. So that's a big topic area, and I'm going to try and condense it all into about 45 minutes, hopefully. All right, so I thought one of the important parts to start with is just some of the framework about timescales in geology, and why that's important is it gives us a framework to understand early processes on our planet. So as geologists, rates are really important, and that's a measure of change, geological change over the corresponding interval of time. And that occurs across a wide variety of orders of magnitude, you know, so we've got things in the electromagnetic spectrum, speed of sound, really fast meteorite impacts, earthquakes, things that we can observe as an event within a human lifespan or even within a day, all the way through to, you know, orogenic processes on millions, if not billions of years time span. The importance of this measure is that the denominator is important because it's over a corresponding interval of time. So what that means is we can have directional processes, and those are extremely rare in geology. In fact, I'm not sure there's any. And that's where the measurement window, so if we take a measurement window of a specific amount of time, that measurement window doesn't have an effect on the rate that's calculated. So we can have a small measurement window or a large measurement window, and we're still going to end up with the same rate of change. But the reality for most geological processes is that they're episodic. And that's really important because our measurement window is then critically dependent, because if I change where that measurement window is, I'm going to get a completely different signature. So that's where the idea of deep time records is really important. Having a record that's long enough to allow us to look at events in their entirety to see if there's cyclic processes within that. So this brings us to the idea of frequencies. So we can have, a background process, but then an event that causes some sort of signal that becomes an important marker for a geological process. If we have a large enough time frame, we can then look at the frequency and the periodicity, where the periodicity is about the repetition of that event through time. And there's classic examples that people will not be offended at hearing about, the idea of Milankovitch cycles. So this is, the progression, tilt, and obliquity of Earth's orbit around the sun has had influences on the sedimentary record, on our environmental record. But, longer cyclic events, we might think about the supercontinental cycle, with this periodic breakup and reaggregation of supercontinents. And this isn't a new idea about periodic events. We can go back to the 1950s. We can go and look at Umbro's thoughts about a pulse of orogenic cycles and sedimentation in Europe. And we can see that, he was pointing out these ideas of periodic mountain building events. But, there's a whole wide range of other different ideas about cyclicity and periodicity within Earth systems. So, are mantle plumes periodic? You do notice there's a question mark there. But we start to see these ideas about 30 million years about the idea of a periodicity in marine fauna and non-marine fauna, and extinction rates, tidal oscillations of the liquid core, dark matter even. Some of the most provocative, perhaps, are the ideas about mass extinctions and their drivers. So that's the large-scale conceptual framework. This is basically where I put up the disclaimer about the ideas that follow, where the ideas are going to be pretty provocative, and we're going to go through a bit of a 101 on astrophysics first, because I think that's important to ground us before we look at the geological data sets. And then we'll look at potential reasons for the periodicities that we see within geological data sets with that astrophysical mindset. Just for a laugh, there are some of the comments various papers within this work has received, and those are legitimate comments. And it's always reviewer two. I don't know why it's reviewer two, but it always seems to be reviewer two. All right, so let's dive into a bit of astrophysics, but I am going to give this from a geological bent, because I do think it's important. I do think these long-scale periodicities are kind of important, and we do want to see in geology if we can resolve, these long-period processes. So what do we know about our Milky Way? Well, we know understanding about our Milky Way is actually really challenging, and the reason it's really challenging is we're right inside it. So how do you observe something you're right inside? It's really difficult. But we can look to other galaxies. So we can look to other galaxies, and there's three main types of design. So there's a grand design, which is basically these arms that are quite well formed, emanating away from a central black hole with these clusters of stars, gas, and dust lined up in these well-defined arms that have a rotational speed. We can also go in the extreme other end member and look at flocculent galaxies, which are where the arms are not as well defined. They're more diffuse. And then, you can get kind of a complex multi-arm system that's between these two designs. So how do we say anything about our own Milky Way? Well, we use radio astronomy, and we use the mapping of atomic hydrogen principally, and we use Doppler shifts to constrain models of galaxies. So here's an image of the Pinwheel Galaxy, which is one of these kind of more classic grand design galaxies with its arms around a central black hole. That's a visible light image. We can look at it from a radio wave image, and you can see it brings out more structure with these bubbles within it, with the well-defined arm regions and maybe, bridges between different arms. So that's the way that we kind of can image other galaxies, and we can take a plane view through our own galaxy like this as well. So what's one of the real important things that we need to know, and if anything in this talk, this is probably one of the most important concepts, is that the arms that we've just been looking at, where we're getting these pile-ups of stars, don't migrate at the same rate as the stars themselves. All right? So that might not seem like a profound statement, but it is. All right, so let me try and explain this and show it with a few animations. What we're basically saying is you can use this traffic jam analogy. So we've got cars and trucks. These are our stars. They're moving down the road, but they're piling up behind a slow-moving vehicle, but they're eventually moving past that slow-moving vehicle. Okay, so we've got this idea of density waves. So we've got a density wave that's migrating down the road, but the individual components within that density wave, the stars, are moving at a different rate. All right. So let's just look at what that might look like. We've got central black hole, we've got material orbiting around that. We're zooming in now. These are individual star systems. The star systems are piling up into the wave and then migrating out of the wave, while the wave is migrating as well. Okay, so the rate that things are moving is dependent on the distance outwards from that central black hole region. While material is outside the co-rotation distance, the wave is moving slower. While things are inside the co-rotation distance, the sun and the solar system is moving faster. Why do we need this process of density waves moving faster than the suns of the star systems themselves? Well, we need that because if we didn't have that, we would have this kind of winding problem, which basically results in the image on the left, which is not like any known galaxies. You see there's this circular pattern. So we don't see galaxies like this. We see galaxies like that on the right-hand side. So this is a model seeded with various star systems spinning around central black hole, allowed to have density waves, and it develops this two-arm system. If we didn't have the density waves migrating at a different rate, we'd end up like this on the left-hand side, which is not a reasonable model. With that said, how far out are we? Well, we're just inside the co-rotation distance, so that's important to remember. So we're moving faster than the density waves. Okay, so there's another type of movement, and this is where we get these, spirograph-like patterns, these beautiful patterns. So this is a geocentric view from Earth of different planets. And you can see, from our viewpoint, it's not a single orbit. It's an orbit that looks to have a changing rate, but that's just from our geocentric viewpoint. From a Milky Way viewpoint, we also have this known as epicyclic motion. So it's a different periodicity caused by the movement of our sun about a guiding center. So we have a bigger movement on top of a smaller movement. All right, let's piece this all together, and I promise that's nearly the end of our astrophysics journey. So we've got a galactic center, black hole, we've got our spiral arms. The classic model for the Milky Way is 4 spiral arms at the distance out that our sun is. Our sun is moving at about 240 kilometers a second. The arms are moving slower. The sun itself has this epicyclic motion as well, and that's at about frequency of 150 million years. And the time between arms, you can see it's migrating between the arms on a period of about 190 million years. Let's just call that 200 million years to make it simple. And we're residing within these arms, which are areas of more stars, more dust, more gas, for about a 63 million year period. There's one other type of motion I need to talk about that's a long period motion, and that's the migration up and down through the galactic bar. So this is the plane of the galaxy, and we migrate up and down through that at about 30 million year period as well. And that's the motion that's been talked about as applying to various fossil records. Okay. With Earth time, we're probably going to focus more on this longer periodicity. Just to show you that geochemists aren't alone at fitting dots and lines together, this is what we have. This is the best, or some of the best data we have really for fitting astrophysical data sets to tell us something about the pattern of our own Milky Way. So you remember I said it's actually really challenging to understand about our own Milky Way because we're slap bang in the middle of it. We're looking through lots of that gas and dust. So we have to use things like parallax between distances to stars. We need to use our atomic hydrogen radio maps to help us piece this together. So here are the primary observations when they've been flattened out into plane of the galaxy. And what we do is we fit logarithmic spiral equations to this, and you can end up with something like that. And those are two different models. We've got a model for a two-arm galaxy, and we've got a model for a four-arm galaxy. So what I would say is that the consensus at the minute in the literature is we've got a four-arm galaxy, but there's complexity in this. It depends on the distance we are out from the central black hole. And these are models, right? They're the best explanations we currently have. And this is the perceived understanding in astrophysics, right? So we're going to head to the geological data sets now. And, you know, we all know about hafnium. It's a very rich data set. It's got lots of information within it. So we have crystallization age of our trusty zircon geochronometer here. We have epsilon hafnium, so that's parts per 10,000 deviation from Schur, the dendritic uniform reservoir. Where we go upwards on this diagram, we have more mantle input, conventionally thought of. Downwards on this diagram, more crustal recycling. All right. The data set itself is beautiful in that, you know, we can fit averages through this, but we can look at some of the complexity within the data set. Is it biased? Of course it is. Geological data sets absolutely are biased. Is it a deep time record? Yeah, it's one of the most deep time records we have. Look at the cratering record on the planet. We're not getting much further back than here. Look at the fossil record on the planet. We're only barely scraping the surface. This is a proper deep time record. That's important, right? Because right back at the start of the talk, I said, you know, we need these long pieces of information to be able to see these long period processes. We've no hope of understanding cyclicity and periodicity unless we've got a suitably long record. So this is where a little bit of mathematical wizardry comes in. So what we're going to do now is talk about the Fourier transform. So the Fourier transform, it's kind of scary math, but I'm going to break it down into something a lot simpler. And what it allows us to do is to take a time signal and convert it into its individual frequency components. So that's the individual signals that we would add together to get the final time resolved signal. So yeah, I like Dundee cake, mainly because it's got quite a bit of whiskey in it. So how do we unscramble all the ingredients that went into this Dundee cake? You know, here are all the bits and pieces. Actually, oh yeah, there's the whiskey, that's an important one, right? So there's our Dundee cake. How do we get back to the ingredients? Well, we use the Fourier transform method. And the Fourier transform method is basically this idea by Joseph Fourier in the 1800s, who said, well, I can describe any kind of process using this mathematical technique where I describe it as a series of circles, and I'll show you an animation. It's not as scary as it sounds. It basically fits a circular statistical approach where we're using the amplitude from and a repetition rate and a starting phase to describe any time series. This guy actually is really interesting. He had a lot to do with the French Revolution as well. Very interesting history. Used this method to calculate information about where cannonballs would land. Okay, so like I said, this animation I think really helps explain what's going on. We've got a very simple signal here on the top, so it's described quite nicely by this circle rotating around. We've got this more complex signal here. We can describe it quite nicely by these two different frequency components, described by these different size of circles with different repetition rates. Look, then we've got this higher frequency signal on top with the blue rotating here, right? Okay, yeah, I can see a higher frequency signal on top of that, and then even higher frequency on top again with red. Okay, so that's a very basic introduction into the Fourier transform to move a time series signal into its individual frequency components. So let's do that. Let's go to two classic examples of early Earth process. One is in southern Greenland, the North Atlantic region, interpreted to be the classic example of early plate tectonic processes on our planet. Let's also go to the Pilbara, conversely interpreted to be the classic example of vertical tectonics, not horizontal tectonics on our planet. And let's transfer the hafnium data sets into their time series. So we take those two data sets, we convert them into the time series, and you can see there's a signal here at about 200 million years. The red line is noise level. The green line is 95% certainty. These are up there. They're actually at 95% certainty. And they're, as we go further to this end, we get into shorter frequencies, and then at this end we're at longer frequencies. So we're in this range here. There is other frequencies in here that have been talked about before, but they're typically interpreted to be the lifetime of an ocean type periodicities. So there does appear to be a statistically significant about 200 million year frequency. I should also point out that if we look at lunar spherules, they also seem to have this strong frequency within it. You might say this isn't that strong. Okay, I'll take that. But let's go and look at a larger data set then. So basically what we're saying is we seem to see a frequency related to the transit between the arms. Larger data set, people call this a tube map. This is a global data set of hafnium in zircon, split by the individual cratons. So what we've done is we've looked at the change points within that data set. So that's when there's a statistical difference within the data set for a specific craton. And we want to do this because we know that individual cratons didn't grow at the same rate. They didn't commence at the same rate, even though they may have gone through the same processes. Their rates and durations have been different. So we're splitting things down, looking at juvenile change points. So periods when that hafnium graph went up, more mantle input for different periods of time. You can see on average, you know, there's a big spike at juvenile crust production at about 2.8 and about 3.3. Those have been previously recognized and ascribed to internal endogenic processes, maybe, you know, early dawn of subduction type ideas. Anyway, what we want to do is break it down into its individual components within this. We have a model for our four-arm galaxy shown here in yellow, and we have these juvenile change points shown here. And we're going to take this apart in a little bit more detail. All right, so we need to introduce a new diagram. So the diagram we're going to introduce is basically using a single orbit of about 200 million years for our planet. So 0 MA is here, and then we're going back in time. So 100 MA is here, 200 MA is here, 300 MA, and so forth, going all the way back to 4.5 billion on a spiral. So you can see that, you know, 0, 1.5 billion years, 3 billion years, all are lining up, and that's because they're in the same spatial position. Okay, so we're able to convert between time now and space on this diagram. This diagram is telling us about where objects are in space in our Milky Way reference frame. Onto this, what we're going to do is we're going to plot that hafnium data. The hafnium data is going to migrate towards the margin of this diagram where there's a higher probability. Okay, so if we look at the solid line on this, we can see peaks in this that appear to overlap these arm passing periods. And that's statistically significant. There is one outlier and only one outlier, and that's the slave craton. And that's been talked about as being a response to early subduction. But lots of the other peaks are within the arm regions. Even more than that, it's not just on one orbit, it's on multiple orbits. You can see the spike here, lining up with another spike here, big spike here, lining up with another big spike here. The kind of more creamy beigey brown color, this is a histogram of craters on Earth, hypervelocity craters on Earth. This only extends back about 1 orbit cycle or 2 orbit cycles. It definitely doesn't get over the full history of our planet. But I would point out again, we seem to get spikes towards Sagittarius, the Scutum, and the Norma arms, which again is aligning with these peaks in juvenile crust production. All right, let's keep with the funky diagrams. We can flatten that out on a, this can be read as time, but it can also be read as space through a single orbit cycle. It's exactly the same data, it's just displayed slightly differently. And what I want you to kind of notice is that things seem to end up piling up on the start of the entries and the exits of the arms. The dashed line here reflects our lunar impact spherules. The solid lines reflect our juvenile crust production on the planet. If we play our Fourier transform technique again, we see a 200 million year peak, just as previous, but we also see this 150 MA peak. The 150 peak, remember, was our epicyclic motion. So we see both these deep time records are recording a periodicity that we can recognize from astrophysics. Now the question is, just because we see a periodicity and an observation of a correlation, does that mean there's a causation? No, of course it doesn't. Let's keep looking at extra data sets to see if we can build a model to explain that correlation. So what we're looking at here is zircon oxygen isotopes. Again, we've got our model for a four-armed galaxy. This is oxygen isotopes from the Pilbara, and I point out where we get bimodality in our oxygen isotopes appears again to be on the entry or on the exits of spiral arms, and it also starting to align with spherular beds. Okay, so this is again, I think, useful evidence to imply that impacting may be having an influence from where we are in the galaxy. There's the timelines again, just placed on for a little bit more context. Okay, so that was a Pilbara data set. Let's do the same thing for a global data set. So oxygen isotopes, what do oxygen isotopes tell us? They tell us something about where melting has happened. It's a proxy for the depth of melting in some respects. Are our melts interacting with the hydrosphere, in which case we would get light oxygen isotope signals, which are low values. Are we taking down bits of crust? That's already seen a sedimentary process that will send our oxygen isotope values heavy, which gives us values higher than 5.3, higher than the mantle value. So again, just like the hafnium data set, the oxygen isotope data set through time, this time series, contains a lot of information, not just within its average value, but within the form of the data set and in its entirety. So what we can do is we can look at the normality of that population. So in other words, is the data all clumped nice and tightly together, or is it spread apart? How peaky is it? Is it a normal shape, or is it a non-normal distribution? And we can look at that through time. Again, here's our model. And what we see is right at the start of arm entries, we get more non-normality in our oxygen isotope data sets. This is particularly strong for early Earth between 3.3 and 4 billion years. This relationship breaks down after about 3 billion years, and I would probably suggest that's because we get more widespread subduction and the internal processes on our planet, so we lose this signal. All right, so we've been comparing our isotopic data sets to models. We've been comparing them to models for a four-armed spiral galaxy. So let's try and go a little bit further. Let's actually try to compare geological data with real astrophysical data rather than a model. And this is pretty hard because, again, we're converting from time to space. So what we can do is take our atomic hydrogen map of the Milky Way. This is basically how we get the spiral arm model that fits to this. and we can orbit the our solar system through that on the correct velocity. So this is what we're going to do. So we're going to take our orbital position just inside the co-rotation distance, and then we're going to migrate our solar system around this, bearing in mind that everything here is rotating. The density wave arms are rotating, and our solar system is rotating. So a little bit of maths to do, but that's okay. We've got computers, we can do that. So we do that, and basically what we get is, over a single orbit, we get this yellow pattern. Now, there's part of this pattern that we can't actually resolve, and that's because we are sitting here. Currently, we can't look through the central black hole, so there is an occluded section. So that means there's a section that we cannot get astrophysical data from. So that's indicated in gray here, but you can see the real data matches our four-arm model pretty well. Pretty happy with that. We can compare it with our oxygen isotope data. This is our oxygen isotope kurtosis, so telling us about the shape of our distribution for oxygen isotopes. And this is summed over every orbit. And that's a pretty good fit. That's greater than 98% confidence. So what do we think is going on? Well, maybe the moon is giving us a good clue. We just need to wait for a nice cloudless night, go outside, look up. The moon is completely pockmarked with impact craters. Maybe we should think about impacting as being a really important process on our planet. And that's been traditionally, pretty difficult for geologists, especially in the early Earth community, because, we don't have craters preserved. What we would point out is that the gravity well of Earth is about 20 times greater than it's 80 times greater than the moon. We're expecting 20 times more impactors on the Earth, even though it's got a more denser orbit. So Earth is undoubtedly going to see more impacts than the moon. So where do we think the impactors are probably coming from? Given that we're seeing a periodic process, we don't think these are going to be coming from the near Earth orbit, the asteroid belt. We think things must be coming from the Oort cloud. So this is the idea of this distant cloud of icy bodies at the extreme kind of limit of gravitational attraction to our own sun. So I did a back-end calculation. So the distance between Adelaide and Perth, if we assume that's the distance between the sun and the Oort cloud, there to there is a quarter of the way to the moon. So we're talking about stuff very, very far away. That's important. It's important because it's loosely bound, and that means it can be easily gravitationally perturbed. And this is the standard model for comets. This is where we think most of our comets are coming from. So this is not wacky ideas. So we suggest that there's periodic disruption of the Oort cloud, sending material inwards into these more Earth-crossing lower period trajectories. If we look at astrophysics, what you're seeing on the right-hand side is a model for the disturbance of the Oort cloud. And there's multiple ways you can disturb the Oort cloud. One of the most widely assumed mechanisms is just the galactic tide. That's basically everything's reacting on everything else. And as you pass through the arms, you would expect to disturb more material. The other one is stellar flybys, and that's the idea that when you move into an arm, you're actually in closer proximity to other stars, and that's supposed to disturb stuff. So what we have here is the most recent representation of what that would do to the Oort cloud. They modeled material being lost into interstellar space, but the reality is more material will also be lost into lower orbits that are going to come out to the left-hand side and head towards the planets. So what's that going to do for us, and why are we seeing that in a crustal evolution record? Well, you have an impact that's going to ruin your day, but what else is it going to do? It's going to cause shallow instantaneous melting, but over a more prolonged period of time, we're going to cause decompression melting. So that's the idea. You pop a bottle on a champagne bottle, it decompresses, and we get melts going up the Adiabat. So we know about this from mid-ocean ridges, how this works. You release pressure, you create a melt, and we suggest this is quite an important process, especially in the early Earth. All right, I think it's only fair to look at some of the criticisms as well of this idea. You know, people will say, but the galactic structure is not stable over time. That is absolutely true. The galactic structure is not stable over time. However, the timescales in astrophysics are actually a lot different to geology. The last time there was a merger between the Milky Way and another galaxy was about 8 to 10 million years ago. Sorry, billion years ago. Geez, order of magnitude there. That's important. 8 to 10 billion years ago. So while the structure is not static, its grand design has been in place for a very long time. We don't think that we expect to see major changes to the structure of the galaxy over the lifetime of the planet. You know, you'd speak to people who work with craters and they'd say, but most of the impacts on our planet are from near-Earth objects, and that's a more constant flux. That's absolutely true. You know, most material that we see comes from the asteroid belt, and that is aperiodic. It's gravitationally quite strongly bound. The material does get lost into Earth-crossing orbits, and this is the more common flux on the planet. That's right. But that doesn't necessarily mean that material coming from here is more likely to cause melting on our planet and to be recorded in the isotopic record. And I can demonstrate that. So this is our cratering record, which is incomplete in this gray area. So this is all model-based, essentially. But we see there's two components. There's a comet flux from distant objects, and there's an asteroid flux. We also see this spike upwards. This spike upwards simply reflects a preservation bias. So there's a preservation bias, and then people say, it's essentially flat until, you know, we get back into the earlier history where we've got this waning flux. And, you know, the idea of the late heavy bombardment now is not really thought to be appropriate. It's this kind of more continuous dropping down to a more constant value. That's all correct for a near-Earth object flux for asteroids, but what about for comets? This is where we need to consider the amount of energy that's coming in. Okay, so asteroids, in terms of the impact flux, is massively higher, whereas comets much, much lower. But look at the average impact velocity. Comets are much higher. And if you normalize out the energy, comets are bringing in approximately the same amount of energy as asteroids. And we would argue that, you know, a cometary signal is a more likely signal to be retained within these deep time isotopic records, simply because our asteroids are near-Earth objects, are producing smaller impacts, lower energy. They're coming in at a lower velocity. All right, getting near to the end, let's just piece all the various bits together. We've looked at various deep time records, pointed out that many of them have a relationship around the entry and the exits to spiral arms. So why around the exit of spiral arms? Well, simply that's a probability function of residing within the arm for a longer period of time, having more gravitational interactions to cause material to be dislodged from the Oort cloud. Why at the entrance? The entrance is where we're literally getting material piling up and forming stars. And I think this is beautiful. We can actually see this process happening, right? This is how we understand how stars form, right? Here's an orbital trajectory through a gravity wave. These are young stars forming, these bright stars forming. But older star systems are migrating through this as well, right? They're passing through this. I think it's only reasonable to think, you know, we're generating new stars here in the same vicinity as passing other systems through this. It's reasonable to consider gravitational interactions may have caused material to be lost. Actualistic models of cratering on the planet imply every spot of our planet has seen one, if not more, impacts. This is important for people looking at early Earth geology. Can we find a smoking gun? Well, maybe we have. Let's go to the center of the Pilbara. Yeah, that looks like a crater to me. The stratigraphy contains shadow cones that are well constrained at 3.47 billion years old, right when we're seeing this deviation in oxygen isotopes. Shadow cones are on a range of scales, up to very large hut-like structures, several meters tall. Beautiful, delicate features with a fractal relationship. Only two ways of causing these structures. You can have a nuclear explosion or you can have a large impact. Just above them, there's probably slavite. So this is an impact melt, I would argue, with clasts within it. Right above that, we've got pillow basalts. Are these a reflection of decompression melting? Right above that, we have banded cherts with stromatolites. This is pretty profound. Are we seeing a relationship between impact craters and cradles for life? Some people have proposed this previously. I think we might have actually found a smoking gun in the Pilbara for that. We're fracturing the planet. We're setting up early prebiotic chemical reactions. We're circulating elements and nutrients. We're bringing in energy. Not only that, we're making these enclosed regions where phosphorus can be enriched. That's key because if these regions are not enclosed, we tend to lose phosphorus. So this is a really nice idea of how we might have formed those so-called Darwin's little pools where we might form life. All right, so I just want to leave you with this, which is, I think as we look into deep time, so we're looking into Archean and maybe even, Hadean geology, we're inevitably going to suffer from a preservation bias. We want to understand geological processes, but many geological processes have a long periodicity. The only way to understand those more long periodicity processes is with a larger temporal window. The only way to get a larger temporal window sometimes is to look outside our own planet, back into other systems that are in a more nascent state. In other words, I'm saying use astrophysics to help us better understand the early Earth history of our planet. That is it. Thank you.
That's great. Are there any questions for Chris? Yeah, Mark?
There were simulations that I've seen showing what could be the outcome of the interaction between the Milky Way and collision.
Sure.
Is there anything in those simulations that demonstrates how rapidly ground design gets reestablished for the galaxies? What sort of timescale of that is?
Yeah, that's a great question. I have seen those designs. I don't know the time frame off the top of my head, but what I would say is that the models that I have seen about the previous merger, the early merger, the reestablishment frequency was on the order of billions of years, but the last major merger was probably about 8 to 10 billion years ago. It stabilized out relatively quickly and well before the 4.5 billion years of Earth history that we have. So part of the challenge that we have is that we're looking at a record for the grand designs, galaxies that are incomplete, but they're also turbulent, right? So, we do think that the Milky Way isn't a perfect grand design, right? We think that it has elements of more flocculent parts, less well-preserved arm structures, broken arm structures, and that creates complexity in our model. But I think it's remarkable that the isotopic records that we have that are truly deep time have a profound and strong statistical similarity both to that model and the real data. And that, for me, well, it's way past chance alone, and I think it's only reasonable to try and explain those patterns with a process. Derek?
So mass convection has its own periodicity to go along with it.
Sure.
And the Earth is There's substantial measurements evolved over time. It's like we live to a more developed tectonic type state, and also as it's cooling, it's probably changing into cooling.
Sure.
How does that affect this sort of process?
Yeah. Sure, that's a beautiful question. So the question is basically for me about the energy coming into our planet. Is the main energy that's within the planet, is that internally produced or is it externally produced? And sure, in more recent Earth history, absolutely, you know, mantle convection is a dominant process that has its own periodicity that we can definitely see the isotopic legacy of in records. But the calculations that we've done imply that prior to about 3.8 GA, the dominant energy flux into the planet is through impacting. The reason that number is kind of interesting for me as an isotope geologist is that if I look at all my hafnium and neodymium data sets, 3.8 is about as far back as you can typically get with those data sets to see extraction from some sort of mantle component. Now, there are a few places that go back further, but they're kind of two places, right? Jack Hills, right, and Acasta, and both those have been proposed to have an impact signature within them. So, short answer is, yeah, sure, mantle overturns and mantle convection does have a periodicity. Impacting, I believe, has a periodicity when were those processes dominated. Greater than 3.8 is impacting, I would argue, based on the calculations we've done after 3.8. I have no problem with more internally derived process dominating. Yeah. You're right.
Factor is very interesting. I mean, I briefly discussed it for emails, but same process basically passage of the sources from Earth to galactic arms. I need to explain the long-term cyclicity of scenarios of record of carbonates.
Yeah.
So I think that one way to costing very large application and temperature. The cyclicity was 140 million years, was minus 50.
Yeah.
Yours used to be longer at 8990.
Yeah.
Is there an argument that maybe the cycle will become shorter over time for the technical
Sure.
Or are we missing something that there's a difference in that cycle?
Yeah. So I think there's two things maybe there. We see a periodicity of about 190, which is the transit between the arms. We also see 150 million year frequency, which is the epicyclic frequency. So that's this rotation as well. The reason that's important is that can modulate when the solar system entered into an arm as well. So it's not just when it's going like that, it's when it's going like that. Two frequencies. I guess what I would say with a lot of the fossil-based evidence is that it is challenging because you're dealing with a slightly shorter, well, actually not slightly shorter, you're dealing with a dramatically shorter record. And that brings challenges constraining the frequency because you've got so many repetitions, you're limited with the number of repetitions you see. So these truly deep time records allow you a little bit more precision around the frequency. And we, you know, the Milky Way itself is, while it's along the lines of a grand design galaxy, it is not perfect. You know, like we just talked about, there's broken arms, there's more nebulous areas. And all that brings this elements of uncertainty, and they increase the plus or minus around the frequencies you see.
Michael, Chris, actually, it's not really at some points that don't remember as bias, right? That's one problem you face. Have you looked at all the records beyond zircons and seen anything like that? I realize small data sets compared to zircon, but anything that you see so far in data sets?
Yeah. So I want to go back to my favorite diagram. So that's a good question. So it's basically a question about deep time data sets in geology are biased. That's absolutely right. You can try and unbias them, but hey, we've only got a sample from where we've got a sample from. So what do you do? But there are other things that we can do. One of One of the things that we can look at are we can look at where the major mass extinctions are. There, 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 there. The 4 big mass extinctions are right on the arms. We can look at where we have spherules, where there's clusters of spherules. Again, they tend to occur on the entrance and exits. We can look at, okay, so this is just the dotted lines here, here, and here are the major peaks in lunar impact spherules. So that was one of the important things that we've been asked repeatedly to do is, hey, the terrestrial record is hopelessly biased, go and look at the moon. We've got so little data from the moon, that's pretty challenging, but where we have got data from the moon, it seems to line up with this. So I've been saying this now, I don't know, for the past 6 years, and it's been a bit of a hard slog. I get frequent emails from people, but I think it's worth seriously considering and has big implications for understanding geology. My personal take is that, you know, plate tectonics and uniformitarianism in geology has been great. It's allowed us to predict a lot of things. Do I think it should be blindly applied to the Precambrian? No, I don't. I don't think that's reasonable. And I think that's something as geologists we should really consider when we're taking processes that we see today and extending it to its full time limit on the planet. Do we really think our planet was a similar processes with similar temperatures, similar atmosphere as the moon at the same distance away? No, it wasn't. You know, why should we expect subduction from, you know, day one? I don't think that's in any way reasonable.
Derek might have to wrap up soon, but yeah.
I've just got one more. This is about the little dynamics.
Sure.
Baked in is your assumption that the solar system is sort of at the same radial distance from the center of the galaxy.
Yeah.
From those models, what are they in? First, those models are looking at the group dynamics, not the what's the chance that one of those stellar systems gets flung outwards or inwards that will change the way this will behave? I mean, I'm sure that adds to the plus and minus.
Yeah.
But it's still likely that a star system will be flung out would actually be in the same position as we want to be.
Yeah. So, you know, that's where I have to defer to my astrophysics colleagues. They tell me that over the duration of 4.5 billion years, 4.5 billion years is a short period of time for astrophysicists, and that's a long period of time for geologists. The process you've talked about is exactly the process that is inferred to disrupt the Oort cloud. So one of those stellar flybys, in other words, an ejection of a solar system out of its rotational distance or slight movement of that, is what's proposed to influence the Oort cloud. If you look in more detail, it's not just a single close fly, they're described as flybys. It's not a single close flyby that's enough to disrupt the Oort cloud, it's multiple close flybys. So all these things sound weird and wacky, but it's like, this is a perceived paradigm in astrophysics. You know, if this is, they say, you know, that this is completely reasonable, this is actually what we expect. In fact, it's the only way that we can rationalize our radio astronomy observations and our distance versus mass diagrams. You know, that those diagrams describe the structure of the Milky Way. They're what leads us to the idea of dark matter. The only way that those diagrams can be rationalized is through a Milky Way structure, which is possibly only with more complexity, 2 arms until close to the co-rotation distance, then becoming 4 arms. So within the proximity of our orbital pattern, it's probably more like a 4 arm.